Okay, let me share my screen. Okay, so this is the first document that was shared to you last Monday regarding the application of first order differential equations to circuit analysis. I think in this case, we have already discussed up to sample problem number 3, right? We're done with number 3 already. Can you give me a reaction if we're done with it already? Okay, thank you, Elaine. So I will now proceed with number 4. The first 3 sample problems here, class, concerns an RL circuit. So the first one is for a source-free RL circuit. We don't have EMF for this particular circuit. And the second one is just another RL circuit, a source-free RL circuit with specific values for the inductance and the resistance. Okay, and the corresponding value of the current is determined or is to be determined using the time here, which is 200 microsecond. For the third circuit, it's still an RL circuit, but class this time, it's not source-free. You already have an EMF of 5, a constant, and you also have the resistance and the inductance. So we're finished with that. And we will now proceed to the fourth example, which is an RC circuit, which has an EMF in volts. This time, class, the EMF is not constant. So it's a function of time, and it is expressed in terms of the cosine function. So your EMF for this RC circuit is 400 cosine 2t. Now, the resistance is 100 ohms, and the capacitance is 0.01 farad. Now, initially, we don't have any charge on the capacitor. So charge is represented in a review as Q. The charge on the capacitor is represented as Q. So at time 0, that is initial time, we don't have Q. So no charge, so that would also be 0 for Q. For this problem, you are to find the current in the circuit at any time t, which in this case requires you to determine the formula or the equation that you will be using in determining the current in this particular circuit. Now, this is an RC circuit. So for the benefit of those who were not able to join us last Monday, I gave you the 2 model differential equations for the 2 circuits that we will have that we will apply first order DE on. So the first one was already used in the first 3 sample problem, and this is our model DE. Okay, for this fourth sample problem, our model DE will be this one. So our mathematical model will be based on the rate of change of the charge of the capacitor with respect to time. So you have Q, and it has also the EMF on the right side. Just like this first DE, it's also first order in form. But whenever this EMF is a constant, or more so even if it's 0, you can actually solve these 2 linear differential equations using separation of variables. It would be a lot easier if you do it that way. But if E is a function of time, just like in the fourth sample problem, you cannot already use separation of variables. Okay, so you really have to process this one or evaluate this using the linear approach. Now, associated with the RC circuit is an expression of the current in that circuit in terms of the rate of change of the charge in the capacitor. So the rate of change of the charge in the capacitor is also the current, is the same current that is passing through your, or that is flowing through your circuit. Okay, and that particular mathematical equation is written here. current I is equal to dq dt. Okay, so these are the equations that we will remember for the capacitor. Okay, in this case, our capacitor is in a complete circuit because I say complete because we have an EMF here, okay, of 400 cosine theta. Based on what is given to you, so I'd like to use the board. That way, we will not have to jump from, and will not have to clear the markings. That way, I can continue. Okay, wait. Okay, wait, class, ha? Let's see it. So this is our RC circuit. I hope you're still there. And we need to write down all this given information and process the DE one at a time. As you can see, since this is already a ready-made solution, this is an outright line in the solution already. But it looks easy because the problem already gave you the equation after this. So meaning, if you evaluate this linear DE, you will have this already as the answer. But it doesn't give you as a student, as a first time, or shall I say, as a new learner on this particular process of analyzing circuits using first order DE, you don't know how did this one came about. So I need to show to you how this came about because it's not as easy when it is presented in the form of a solution like this. The case of solutions that are also presented in solutions manual. So I will go to the board and write down our information for this particular problem. Now, since we're given an RC circuit, you're going to start with the model DE for that RC circuit. So it was shown to you a while ago that our model DE is dq dt plus 1 over RC times Q, and it's equal to E. It could be a function of time or it could be a constant over R. Okay? This is our model DE as shown to you. So this is it. Okay? And this is the model DE that I started with, this one. Now, in that model DE, I need to substitute the values that are given here in the problem. So I have the EMF. So I will write the EMF now. So in here, I'd like to write 400 cosine 2t. Okay, now, and then about the R. So your R, in this case, your R is 100 ohms and the capacitance is 0.01, excuse me, farad. So 100 ohms and 0.01 farad for the capacitance. Okay, so we'll substitute it in here in our equation. So we have here 100 and I have here 1 over, so it's 100 times the capacitance in farad, which is 0.01, and I have here the Q, and this is dq dt. So I have placed in the values of the resistance, the capacitance, and the EMF in our model DE for an RC circuit. Now we will simplify, so this becomes dq dt plus, so this is actually 1, so you have a Q, and this one, to get the 100, the zeros, this would be 4 cosine 2t. In here, you could see that your DE is linear. Okay, it's linear in form. And you could see that your P of T is the coefficient of the Q here, and it's 1. And your Q of T is all of this. So you have 4 cosine 2t. So if you're going to use the linear approach, because this cannot be evaluated using separation of variables, then you need to determine the integrating factor. So the integrating factor phi is equal to e raised to p of t dt. Now, when we were solving linear DE, we determine it based on the formula e raised to the integral of p of x dx, because our independent variable then is x. So this time it's not x, it's t. Okay. Now, in some books, this integrating factor is represented by mu, not as phi. So it's the same thing. Actually, it's really dependent on you on what particular representation you want to use. As long as you define it, that's your representation for the integrating factor. So for a linear DE, you've learned in midterm that the formula will be the unknown function. In that case, our unknown function is q times the integrating factor, and it should be equated to the integral of the q of t multiplied to the integrating factor dt. So this will be our guide in evaluating our first order DE. So I will have the Q again. The integrating factor I will copy. If this is evaluated, actually, this will be e raised to t. So I'll write here e raised to t. Now on the right side of my equation, I will have the Q of t. So what's the Q of t? So our Q of t is 4 cosine 2t. So I'll place here 4 cosine of 2t. I'll multiply it to the integrating factor e raised to t dt. Now, upon looking at it, it's an integral that can be evaluated using integration by parts. But if you have already a ready-made formula that you have learned in your math 12 then, or EMA 103 then, how was it, EMA 102, because you're now in EMA 103, then you can use that. Now, in this case, if you're going to use the fundamentals of having to use integration by parts, so I will set aside the constant, and you have this one to be evaluated. Okay. Now, if you have this, if this is the thing that you're looking for, the integral of the cosine of t dt, I'll write it here using integration by parts. You have a choice whether it would be e raised to t that you will use as u, and the dv will be the rest of the expression here, or the other way around. In this case, I think it's easier, excuse me, if we make the u be the e raised to t, and the dv being cosine of 2t dt. Now, if this is our u, your du is e raised to t dt. And your dv, if we intend to find the v, will be, of course, 1/2 sine of 2t. Now, using this, you can rewrite this integral of cosine 2t e raised to t as uv. So the product of u and v, so that would be 1/2 e raised to t sine of 2t minus the integral of v du. So that would be 1/2 integral of e raised to t sine of 2t dt. Okay, so I multiplied these two in here for your integral. If you look closely, this one cannot be evaluated again, so there's a need for you to do another integration by parts. So we will do that. So you will have another u in the form of e raised to t, and a dv in the form of the sine of 2t dt. Differentiating the u, so that just like the one that we had a while ago, so it would be e raised to t dt, and integrating dv, that would be negative 1/2 cosine of 2t. Now we will replace this integral that we have here by the equivalent two terms of this. So I will now, so that we can see clearly, I will write now the integral of cosine 2t times e raised to t dt equal to, so our first term here, I'll copy because anyway, it's not an integral. So 1/2 e raised to t sine of 2t. Now for the second term, this integral here will have equivalent two terms and it has to be multiplied by negative 1/2. So I'll place negative 1/2 and it will be multiplied to, in that case, uv. So negative 1/2 e raised to t cosine of 2t. So you have negative 1/2 e raised to t cosine of 2t. What about the second term to this? So it's uv minus v du. So if this is negative, that would be making it positive. So plus 1/2 e raised to t cosine of 2t dt. So remembering that, you write here plus 1/2 e raised to t. So that would be integral, by the way, cosine of 2t dt. Okay, so this is your uv minus v du. So this becomes positive because in here, your v is negative. Okay, I just simply copied the product of these two and reflected it here. So if we will simplify, we have now 1/2 e raised to t sine of 2t. Now this 1/2 and this 1/2 negative, that would make it positive. 1/4 e raised to t cosine of 2t. And this, that will make it negative 1/4 integral of e raised to t cosine of 2t dt. Okay, this is all integral. I hope you can follow through. This is already finished last time. So this one is similar to this. It's e raised to t cosine of 2t dt. So if we will combine this one with this one, this is 1 here, and this is 1/4. So if we'll add, because it's negative in this side, that would be 5/4 integral of e raised to t cosine of 2t dt. I now combine this one with this. So I'm left with two terms here on the right. Now, since we are after, since we are after the integral of e raised to t cosine of 2t, so that's the one that we're trying to find. In here, I will divide, or I can multiply this entire equation by 4/5. That way, this becomes 1, the coefficient here. So then I can have integral of e raised to t cosine of 2t dt being equal to, after multiplying this entire equation by 4/5, that would give us, so 4 divided by 2, so that would be 2. So 2/5 e raised to t sine of 2t. And this will cancel each other, so that would be plus 1/5 e raised to t cosine of 2t. Do you follow, class? Positive, correct. Okay. Now, this one will be substituted here in this side. And I will copy this one. So now I can write here on the next page, the q times the integrating factor is equal to 4, because we have this 4, and whatever is this one, the cosine, or rather the e raised to t cosine of 2t. And that is this one. So I will copy this. Now in here, you could see that I have an exponential function that is common, and a 1/5 also that is common. So I can factor it out. 1/5 e raised to t. So I'll place here 1/5 e raised to t. Then my multiplier for the first term would be 2 sine 2t. So I'll place here 2 sine of 2t. in the second term, if I'll take 1/5, so that would be only cosine of 2t. I'll take this one also, so that would be cosine of 2t only. So plus cosine of 2t. Okay? Now, you have an e raised to t here and an e raised to t here. You can take it out. Actually, however, class, let's not forget that in here, this is an integral, an indefinite integral, and there has to be a constant of integration c that should be placed here. So I'll place here c. If that is the case, then we are not allowed to cancel the e raised to t. What we can do is we can divide by this. That way, we isolate the q expression on the left side. So if we will divide, by e raised to t, now you have q left on the left side, and you will have 4/5 e raised to t, and then it will be multiplied to, this is already canceled, so it's not supposed to be written there. So 4/5 only. And we have the multiplier. In the case of 4/5, we have the multiplier to sine 2t. In here, we have plus cosine 2t. And since we are dividing by this one here, this one will have c e raised to negative t. You get it? So this will be c e raised to negative t because we are dividing by the exponential function e raised to t. Now, this formula would have been a complete formula if not for this arbitrary constant of integration. So we need to determine the value of this. That way, we will have an exact formula for the charge. Okay, so how do we evaluate or determine the C? We use the initial condition in the problem. So it was stated a while ago that initially, let me share to you the problem. That way, you will understand what I'm trying to say here. Okay, we'll just share again. Share. Okay. It says here that initially there is no charge on the capacitor. So that's the initial condition that you can use. That way you can find the C in our integration process. That way our Q as a formula will be complete. It does not have any arbitrary constant. Okay, so we'll go back to our board and substitute that initial condition. So at t equal to 0, Q is equal to 0. So it will now be 0 equal to 4/5 times 2 sine of 0 plus cosine of 0 plus c e raised to 0. Now the sine of 0 is 0, whereas the cosine of 0 is 1. Though we can see here that we have 1 and 0, so that would be 1. So we have 4/5 plus this c here, because this one is 1, c. Now from in here, now we have the value of the arbitrary constant. So c is negative 4/5. Okay? Now, since we know that that is already our C, you can go back here in your formula and substitute this one. So I'll write it here in the next page. So we have, so 4/5 and all of this, we will copy. Okay, I hope I got it right. 4/5 to cosine of 2t. Oh, I got it interchanged. 2 sine of 2t plus cosine of 2t. I got it interchanged. So this should be sine and this should be cosine. So this is sine And this should be cosine. Okay, we're copying it from here. And this one will now be changed to negative 4/5. So you have negative 4 over 5 e raised to negative t. Okay, this is the formula for this given circuit that you can use to determine the charge in the capacitor at any time t. So all you have to do is substitute the time here in seconds. But the problem, class, is the problem is not asking for the formula for the charge in the capacitor. What it is asking actually, if I'll go back to it, it's asking for the current. You find the current at any time t in the circuit. This one, find the current at any time t in your circuit. So anybody here who can suggest what do we do since, if I go back to our board, since what we have processed so far is a formula that will only allow us to solve for the charge. How do we find the formula that will allow us to solve for the current? Since this one is for the charge. Okay, somebody wrote, very good. So you have to differentiate this given equation because a while ago I showed to you that but current is equal to dq dt. So if I want a formula that will solve for the current at any time t in the circuit, I will just differentiate this with respect to time. So my current now, for my circuits, that's I of t, I can solve for it at any time t, is equal to the derivative of q with respect to t, and that could be this one, differentiated. So I will just differentiate this one. So I will have 4/5 multiplied to, if I will differentiate the sign, that would be giving me a cosine, but don't forget the 2 in here. So you will have 4 cosine of 2t. This one will yield a negative sign. So this would be minus 2 sine of 2t. Okay. And for this is negative. So in terms of its derivative, that would be multiplying it with negative 1. So this becomes now positive. So plus 4 over 5 e raised to negative t. Now you see that this 4 over 5 is present in both sides. So you can write current now. The formula for the current in the circuit as 4 over 5 times. So you may opt to write this one first. E raised to negative t plus 4 cosine of 2t minus 2 sine of 2t. Now this is the expression that we are looking for, that expression which allows us to solve for the current in your RC circuit given the time. So whenever you solve problems like this, class, before I miss mentioning it, although it has to be fundamental knowledge, that your mode of your calculator should be in radian mode. Why? Because when you multiply the 2 in here to the time value that is given in the problem, the argument of your cosine, the same thing with the argument of your sine here, will be radians. They are not degrees. So then your calculator has to be in radian mode. So just make sure as well that the time unit that you have in here is seconds. Okay, so far, this is the answer to our fourth sample problem on the RC circuit. Do you have any question? Okay. Miss, okay lang ang capacitance nga 10 raised to negative 2 di pag-convert. It's okay. It's okay. If you will not convert it to times to 0.01, when you multiply 10 raised to negative 2 to 100, it would still be anyhow 1. So it's okay. Okay. Any question? Is this clear? I'd like to go through some of the documents I've shared to you. They have all solutions. So since we have time, I can go through them now until we run out of time. Any question? Okay, if there's none, so I'd like to, okay, there's one here. To clarify, Miss, if there is no presence of voltage source in the circuit, Miss, we only have transient current. Okay, to clarify as well, your current for an RL circuit, you may be referring to the RL circuit. Your current for the RL circuit, if it's a complete circuit, will have two terms, the transient current and the steady state current. Now, if your question is if there is no presence of a voltage source, automatically the current that you will be computing is the transient current. If it's free, if it's source free. Pero kung imo gid siya i-set up na do pareho lang bala hindi siya source free, ma-substitute ka gigyapon sa imo nga main DE. What I mean is nga hindi ka mag-rely sa imo nga pre-derived nga solution, the right side would still be 0. So if you will process it, it will still come up with an expression that has only one term on the right side. And that is still your transient current. So if it's a voltage free source, if it's source free, wala siya sang source, then automatic the current that you will have is just a transient current, no steady state current. Any question? Some more question? Okay, if there's none, I'd like to share to you some of the files that I also shared to you in Canvas. We have our sample problem number 1 is a source-free RL circuit. Now, I shared to you a sample problem wherein you have a source-free RC circuit, and this is it. I hope you can see it because it's already open here on my side. Wait, I'll start here. Do you see it? Can you see it? This was shared to you in Canvas. Do you see it? Okay, thank you, Jayan. Now, the upper part or the introductory part of this document still reviews the things that we have discussed last Monday. So it reviewed the things associated with the capacitor, the charge on it based on this formula, and the current on it passing through it based on the rate of change of the charge, or it could be also a current in terms of the rate of change of the voltage. So the two different representation of the current in your RC circuit for that matter. So you have two, okay? One in terms of charge and the other one in terms of voltage. Okay, the rest of the terms here or the rest of the expressions here only defines the units for the I think we call this the unit of the capacitance, the charge, the voltage, and the current. Anyway, you know them already in your physics. Okay, and this was also discussed last Monday. Now we go to a source-free RC circuit because we have an example already for RL circuit. In this case, we don't have a source. So if we will do nodal analysis on this particular node here, this node, the current leaving this node, the sum of the current leaving this node should be equal to 0. Okay, no source. So if that is the case, this is your equation. Current passing through your capacitor is equal to the current passing through your resistor in here based on this node analysis. Now it's equated to 0. Now based on our definition of the current here, we have this definition of the current. We replace the current in the capacitor by C dV/dt as written here. And as to the current in the voltage in the resistor, that is taken from the formula of the voltage drop across the resistor. that voltage drop is V equal to IR. So if you want the I, that would be V over R. So you have this one here. Okay? So this is after you have substituted. Let me close. That is after you have substituted in this expression. Now, this one as written is linear, but actually this can be used, solved using separation of variables again. So if you solve it using separation of variables, actually it would be a lot easier and more straightforward. Let me show you. Let's say, for example, I will not treat this as linear. I will solve it using separation of variables. I'll transfer this on the right side. So that would be negative 1 over RC times voltage. So I can transfer the voltage here, the V, and I can transfer dt in here. So that expression would be dV over V equal to negative 1 over RC dt. Right? Separation of variables. So you can integrate right away. And you start here with the initial voltage. So we represent it as V sub O. And the final voltage at any time would be V. On this side, your initial time is 0 and your time at any time will be T. If you will integrate this one, left and right side, the resulting expression would be the ln of V over VO equal to negative 1 over RC times the time. If we will simplify by making this expression here the exponent of the E, the left side becomes V over V sub O, and the right side, of course, will become exponential. T over RC. Simplifying further, you will have now a formula that will solve for the voltage across your capacitor at any time in terms of the initial voltage of the capacitor and this one. You have T over RC. So the V sub O was just cross-multiplied here to give us a formula for the voltage in the capacitor at any time T. If you look closely, class, I'll go down. Ari na siya, oh. It's here already. V is equal to VOE raised to negative T over RC. Here it is already. Okay? Now, this one, this formula for the voltage across your capacitor given the time is comparable in form to what? The current, this one is the current in the RL circuit, source-free RL circuit. If you look very closely, they are very similar in form. Only that in here on the left side, you have current. In here, you have voltage. And your exponential function, of course, differs in the argument that you could see. The REA, you have negative R over L. The REA, negative 1 over RC. You follow? This one is for the RL circuit, source-free RL circuit, solving for the current. This one is for the source-free RC circuit, solving for the voltage across it. Okay? Now, if you recall also last Monday, I have shown to you the behavior of the current in a source-free RL circuit as time increases. And it's an exponential decay. The shape of the curve is similar to this one. So this curve this time does not give you the relationship between current and time, but this time it's voltage, V. So we have V here, and this is time. So you can see that there's also an exponential decay or decrease in the case of your voltage across your capacitor as time increases. Okay, now the same thing with you if you recall the tau in the RL circuit. Who can give me the tau for the RL circuit, the time constant? What's the formula? Let me see. It's L over R. Correct. It's L over R. What do you think is the tau formula for the RC circuit based on the formula here? What's the tau? Because you could see here that in the graph, it would take this tau time for the voltage across your capacitor to decrease to 36.8% of its initial value. What do you think is the formula in determining the tau for this RC circuit? Let me see. Correct. So si Elaine lang diguro akong estudyante ay. What about the others? So if in RL circuit, the tau is the reciprocal of what you see here in the argument. Oh? Di ba la ang L over R, reciprocal yan na? So there is sa inyo RC circuit, the tau is RC, the reciprocal of 1 over RC. The same unit, so the unit will be in seconds. Okay? Now somebody wrote here, I think it is the reciprocal of the integrating factor. It's the reciprocal of the argument here. Okay? That's correct. So it's RC. Okay, now, remember you have this formula for the voltage across your RC source-free circuit. And you have this formula for, okay, allow me to erase my markings here. And you have this formula for the charge. And if you want to change the V here, remember the V is this. So if you want to change the V, the voltage here in this formula for the charge in terms of time, narin na siya, oh, in terms of time, you may do so. Now, you have C V sub O e raised to negative T over RC. However, your C times V sub O based in here is actually the initial charge in the capacitor. So now you have a third formula that is so similar, like 99% similar to this. Look at it very closely. What happened? You just change the voltage to charge. You have the same exponential function appearing on the right side of the equation being multiplied to the initial charge in your capacitor. So you have this formula to use for source-free RC circuit for the voltage and this one for the charge. Hindi man budlay memorizon kay actually pareho sila itsura. Ginislan nyo lang ang quantity nga ari dire. Direya voltage, direya charge. Okay? Now, I will proceed that. Just interrupt me if you have any question. Now, what about the current through this source-free RL circuit? Di ba ang gin-derive ta diya voltage niya, oh? Non-voltage kag charge? How do we get the current? So, pareho, gito kaina sa aton example number 4, right? We determine the current based on the derivative of the charge. Based on the derivative of the formula for the charge. If this is your charge, you can also get your current from that. Where is it? Here. So dq dt, so you determine the derivative of your q, this one, with respect to time, and that would also be your current in the source-free RL circuit. What you see here on the right side, class, is just the differentiation that happened in here. Okay? Derivative man lang na siya. I think I need not explain that. This is the derivative. So Q sub O, EU, you copy the EU, then the DU of the EU, which is negative 1 over RC. Then simplified. You have to simplify. So you have negative B sub O. Again, you see this one. Q sub O over C is B sub O. From the, let me annotate. So you have QO times CV. So your Q over V is C, or Q over C is V. So this one, Q over C was replaced by this V sub O. because this is Q sub O. R was copied coming from this. And the exponential function was just affixed to it. This is what you learned in sample problem number 4 a while ago. How to determine the current in your RC circuit by differentiating the equation that you have for the charge. Another way of doing it is kay since duha ang aton nga expression for the current, we have two choices for formulas for the current in our RC circuit. You can use this one as well, wherein you have I, the current, equal to C dB. Di naman na siya mis naghalin. Hari na di siya kaina sa babaw-babaw. Gid. Ari siya ho, C dB. Okay? So if you do that, if you use that particular expression, you have C dB, and this V now will be replaced by VO, E raised to negative T over RC. From the formula we have here. Okay? Ara na siya gin-substitute sa dira. And then the rest is your differentiation process, which yields this one, and you have this. So anong natabo? Either which route you pass through, what I mean route kung sa aton language, miski diin ka maagi, mo man nagyapon ang resulta niya. Whether maagi ka sa diri nga formula or you differentiate right away the charge, you will still arrive at the same expression. Oh, the same lang sila oh, ining duwa. For the current in your source-free RC circuit. As to the behavior of this particular current, okay, I need to erase and so I can go up. You have here B sub O over R. The vertical axis is B sub O over R, and this is your time. In the case of the behavior rather of the V sub O over R to time, as your time increases, your V sub O over R decreases. Igapanaog siya, oh. Or rather, if this is the negative side, by the way, it increases. So from the bigger negative value, it will now go down, go up. So meaning it becomes less and less negative, meaning it is increasing. Because if you have a negative value and it becomes less and less in numeric value, its value is increasing. So as time increases, the ratio of the V sub O to the resistance increases as well. Because initially it's negative with a higher value, but this time it's now approaching the horizontal axis in an exponential manner, but it is increasing. Now, having learned this, it's important that you know how to write your formula for a specific circuit that we have discussed so far. So in your case, you have an RL and an RC circuit, and you have ready-made formula for a source-free RL circuit, and you have a ready-made formula for a source-free RC circuit. You list them down on a paper. That way you have summarized those. That way, when the need arises during the quiz, that you need only to go back to those pre-derived formula, you may do so. It's not required anymore that you show your DE, because anyhow, it was already discussed how the formula were derived from the model differential equation. Okay, that way during the quiz or the exam, you need not go back to your notes and leave Canvas. And that way you will see that, then I will see in the log that you are leaving Canvas already. So it will help also in your studying if you will make a summary of the formula that we have discussed already for your RC and your RL circuit. Now I have examples here for that, the illustration of this particular concept. I leave that to you to read. If you have any question, you may raise your question to me anytime tomorrow during the day before you have your quiz in the afternoon. Okay? Now, another document that I've shared to you in Canvas is this one. This is for the complete RL circuit. Actually, I gave already a sample problem wherein the circuit is not source-free. in the RL circuit, and that is sample problem number 3 in here. Ari siya, complete ni siya. May electromotive force kita. So diri, it was just being illustrated clearly. It was discussed. And you have here the manner of determining the current in that particular circuit. And we have this already. Atunan nito siya sa sample problem number 3. Now this one. What you have here is just the formula. And by the way, class, this V sub S is the voltage in the voltage source. Okay? Divided by the resistance, if you're wondering what it is. And you have also the concept here of the natural transient source-free response reiterated. And you have the forced steady state response in here. It was also discussed in sample problem number 3. Because in number 3, you already have two formulas. Duwa na to inyo, no, not two formulas. You have two terms on the right side of your current formula. The one that was mentioned by your classmate a while ago, the transient term and the steady state term. Okay? The steady state or the forced response. The natural or the transient source-free response. Okay, that was asked a while ago. This is your complete response for your complete RL circuit. Okay? And here you are given how the behavior of the ratio of the voltage to the resistance behaves with respect to an increase in time. So you could see an exponential increase. Both are increasing. If time is increasing, the ratio of V sub S, or that would be your voltage divided by the resistance, will be also increasing exponentially. Okay? Now, you have here additional formulas for the voltage in your inductor. I leave that to you to read, and you have sample problems here. And which brings about, class, in the other, shall I say, where is it? In the other documents that I've shared to you, may-ari na the sample problem na may impedance. Where is it? The Z, I think it's in the RC. Don't bother to study that one because it's not anymore included in our discussion. So we'll only limit to the current, the voltage, the charge if we have an RC circuit. We're not anymore concerned with the impedance. That would be discussed to you by your department chair. When you reach already circuit analysis, that's where you really be trained how to analyze circuits. Our main goal in DE is for the students just to understand how your first order differential equation could be used in the analysis of simple circuits. Amo na duwa lang ang elements at a time. So we can have R and L, or we can have R and L, or we can have R and C. So you can view these particular documents later or tomorrow, and then should you have any questions and clarification, feel free to ask me. Okay, I will stop sharing now. It's 2:27. If you have any question, you may raise them as well regarding anything concerning DE. You have any questions? I will have this particular discussion uploaded later. Actually, I already discussed this with the ECE, and it's the same thing with you. But I think my coverage to them is bigger this morning because we were not able to reach until third sample problem. So I will have this sliced again because this part is not part already of the link that I am to share in YouTube. Included miss and heat transfer. Yes. It's good that you asked about heat transfer.